helps. But welcome to the third session. I'll quickly go over the intro stuff as I have done the past couple times. Follow along in the online course material. For this session and the next session, you might want to refer to the online material a lot more. There are visuals in there that we made that aren't in the presentation because we can't put them in, that can help get a bit of a better understanding or intuition for how some of these objects we're going to see actually work. And I'm going to expand more on why that's so valuable. Yeah, if there are any issues, mention in the channel. The side chat's working, unfortunately, so I can see questions as soon as. Clarification, nothing against to me. If you have any questions, now's the best time to ask them. Also, still from session 1, because of course it wasn't easy to ask questions last time. I think a question is being written, so I'm just going to wait. The online material link is there's this link with HackMD with all the stuff, and the link to the book is there as well. That's probably the best place to start. Okay, cool. Then it seems like there's no questions from the previous sessions or lingering things that weren't entirely understood, so we'll just press ahead. Welcome to lesson 3. Just prior to actually the content, we want to discuss the meta of why we're doing this. To work in the ZK space or cryptography in general, I don't know what your backgrounds are or where you're looking to go, but this is a ZK course, and it's not general cryptography, but if you're interested in ZK, you might also be interested in general cryptography. There's kind of 2 hard skills that you probably want to know very well. And one of the reasons why it's such a good job and commands because it requires 2 hard skills. Like learning one of them is obviously maths and programming. You do people who are very good at the maths. Generally speaking, they're probably in academia and things like that, doing research, and it's very hard to to get a role like that unless you go down that exact path of somehow doing a PhD or just finding lots of research jobs. And I think there are far fewer. And for people who just do programming, you can't. It's not really wise to code cryptography without knowing the maths as well, because for one, you can't understand what the paper says or the things it talks about because it's written in the language of mathematics, and 2, there's lots of things that you have to know in order to make sure what you code is safe and secure. So you do want to know both of these skills to be doing this kind of job, because most of the ZK jobs are applied ZK. It's take a look at the space, look at the different proof systems, look at the different protocols, try and figure out which ones to use, try and optimize parts of it for your own system or create things from scratch, and code it, obviously. So you do want both of those skills. I guess some people come out of university with both of those skills, but I think by and large, most people come out with one of those skills and learn the other. I think it's easier to, study maths and then learn programming afterwards. But yeah, of course, if you already have one of those skills, you're not really going to be going back in time. But the better you know the maths and the better you understand it fundamentally, the easier all this is. Like without the maths, if you look at these papers, they just mean absolutely nothing. Even with like a strong mathematical background, once you start reading these papers, they're very tough because there's like theoretical computer science type stuff, that's hard to understand. But the better you have these fundamentals down, the quicker you can make your way through things and be a better ZK, applied ZK person. The things we're going to cover here in this session, not on Thursday, we'll do some other stuff then, is something called modular arithmetic, something called groups, something called fields, and something called polynomials, which we actually touched on briefly before. These are like the most fundamental building blocks. Some of the definitions, well, I think most of these definitions are actually fairly straightforward, but you can just do so much with these objects that there's loads to learn. And we're only going to touch on kind of the most fundamental definition aspects of them. If you go on to do advanced courses, you want to know these objects like really, really well, and they'll just be doing much more advanced things with these objects, showing much more special behavior of them. So seeing these now will be very helpful before you go onto a harder course. And some of this hopefully should actually be familiar to you. If you're a programmer, the modular arithmetic part should be clear. There's actually I deleted it off the list, but we'll do a fifth part as well called the Schwartz-Zippel lemma, and there's a very important theory that actually gives us the percentage of proof of the probability of a proof passing. Okay. And I discussed why we chose PLONK in the previous session, so I'm not going to discuss that again. It's just a very good one to start with. And we're also kind of choosing the maths based on going towards understanding PLONK specifically. The different proof systems will require different maths, but by and large, there's like categories. There's like PLONK-like proof systems where if you know this math, you know that stuff. And then there's a bit of overlap with kind of SNARKs. You'll need to learn some other stuff for the SNARKs. But once you know one of them, you could the other kind of SNARK-like systems you can understand much more easily. So it's not like you have to learn loads of new math for every single proof system. There is a lot of overlap. Modular arithmetic is the starting point, and it's sometimes called clock maths. And um, do ask me questions if parts of it aren't unclear, because this is the kind of thing I did so long ago and was so fundamental. I can't necessarily remember the things that people struggled with this when they first learned it. Even I would have had issues when I first learned it too. But basically, you're going to count up to a number, and you just hit an upper limit, and instead of going beyond that, you're going to loop back to zero. And if you're a programmer with like I8s or U32s or any integer value, you know that you'll wrap around. So with an I8, you'll get to 255, and instead of going up to 256, you'll go back to zero. And that's the exact thing we're going to have here. But we're kind of defining it in a mathematical way as an actual sort of set. So this is the kind of picture thing. There's an animation on the web material, so it'll be very helpful to see the animation and how you step through. But we basically have a part of the number line from 0 up to some number, and it's a whole number, like 11 in the image. It could be 0, 1, 2, 3, 4. This is not a continuous. It's not a continuous length. We don't have 0.1 or any of the numbers in between. We just have the whole numbers. Yeah, I mean, in programming terms, the -1 index will be the last number. So in the set 0, 1, 2, 3, 4, the -1 would be the 4, and in the 0, 1, 2 up to 11, the last index would be the number 11. Well, technically 10 actually. Yeah, and this is kind of it. So I'm going to sketch this, but when we count up, instead of counting past our limit, whatever we set it to, we just loop back round. Where's the thing? There we go. So this is called modular arithmetic. If we take this set I gave, 0, 1, 2, 3, 4, this does have 5 numbers, right? Because we start at 0, even though it goes up to 4, the fact that we start at 0 means we have 5 numbers. Alternatively, we can sort of draw the number line, that's the 0. And I've got to decide here whether to draw a 5 or a 4, because it seems like these things aren't the same. But because we're going to wrap this round into a circle, 0 and 5 are the same number. So even though this line goes 0, 1, 2, 3, 4, we're not very well spaced, obviously, 3, 4. Even though it goes up to 5, it doesn't include the number 5 because 5 is treated as the same thing as 0. 1, 2, 3, 4. 1, 2, 3, 4. So if we're going to count on this, we'll go 0, 1, 2, 3, 4. is that if we set, let's say we want 5 numbers, then set 5 to be the same as 0. And you'll see here I used, in this equal sign, it has 3 lines. And that's like a specific mathematical notation that we use in these groups, because if I'm to expand that out, we use this under the scenario 0 mod, modular arithmetic, 0 mod 5. This 0 mod 5 is telling us that in the set that we're working in, we're treating 5 to be the same thing as 0. Now, if it's your first time seeing this kind of relationship, it might just feel strange and, out of the blue and a little bit uncomfortable. And you'll just get used to it. Like, there's nothing really deeper going on. It's just that we just treat 5 as the same thing as 0 because we imagine it as this clock. And there's no reason it had to be 5. We could choose any number. We could do a different example with a. So this previous one is called the like mod 5 kind of example. We could do a mod 7 example, and then of course it would go 0, 1, 2, 3, 4, 5, 6, and we could say it's 7, but actually we know that's the same thing as 0 mod 7. Similarly, if we start to do more than just count, if we do our normal operations that we're used to from normal maths, let's say 4 plus 5, well, that equals 9, but 9 isn't a number in our set, so we can't say that it equals 9, so we've got to do something else. And we can see that we can just remove, well, not remove, but we can decompose this, because 9 is 7 plus 2. But we know that 7 is 0, so this will be congruent to 2 mod 7. Yeah, so all our normal maths still applies. We can add and multiply numbers and still be in our set. Similarly, if we do a multiply, 4 times 5, obviously we get 20. Plus 7 plus 6. Well, we can, but we can just do it more quickly by seeing the number of 7s, which is 2 times 7 plus 6. But we know that all the 7s are the same thing as 0, so this is just the same thing as 6 mod 7. Yeah. So if we draw it all, our clock as we had before, we have 0, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Then if we're to do the 9 example, we count up to 4, and then we go around 5 steps. We go 1, 2, 3, 4, 5. You'll see that we ended at the 2, which is why we had this 2 mod 7. Okay. Now, I don't know your backgrounds, like if you're programmers and you work with, I8s and things like that, and you've seen this kind of thing before, this might be extremely easy for you. But we're defining it much more clearly in sort of more mathematical ways. It's called modular arithmetic. We have this notation with this, triple line equals, which we say it means it's congruent to, and we define the group we're working in to be mod 5. Okay. So we go on to our second object, and these objects actually just kind of keep building on each other and get more complex. So groups take modular arithmetic, and what they do is they add more structure to it. Modular arithmetic sort of told us the relationship between the numbers, but a group takes a set, which is the modular arithmetic set itself, and then it adds some other things. It adds a bilinear operation and an identity element, which sounds like gibberish, but it is like very real mathematical terms, which will make sense to you soon. But this is a very abstract way to think about this stuff, which is also why it's so valuable. So what are the objects inside it? I said we had this set of numbers. We can do 0, 1, 2, 3, 4. We can go 0 to 10, which would be 11 numbers, or whatever else we want to choose. We'll have a binary operation, and what that means is it's an operation that takes in two things, which is why the binary part of it is there. So addition is an example, binary operation. You take in two numbers and you add them together. Multiplication is another example. But in a group, we only have one binary operation. We'll choose which one. And it might seem like that's it in terms of the types of operations, but you can define arbitrary binary operations. For example, you could define a power one. So if you take in A and B, you'll do A to the power B, like 3, 2 would be 3 squared. And that has very different properties. Or you could just modify a normal, addition or multiplication. Instead of doing A plus B, you could do A plus 2B, which is still a binary operation. And it's not addition as we know it, but it is still something we could put in for our group. And then we have something called an identity element. It means that when you put it in the binary operation, it does nothing. Okay, so that's much easier to understand with an example. What does nothing under addition? Well, that's the number 0, because 3 plus 0 is 3. Any number plus 0 is the same number that you started with. Yeah. And if arbitrary operations, the way multiplication is made from addition, we can see multiplication as being made from addition, but yeah, you can make it in different ways. Like arbitrary just means that as long as it's a binary operation, it doesn't really matter what it does. Even if it does something really odd or boring, it just has to be a binary operation. So arbitrary is also a word used a lot in mathematics, and that just means that you have like a huge set, or maybe a finite set that you can choose from. But the point is, it doesn't matter which one you choose, as long as it is something from this area. As long as it is a binary operation, any of them, doesn't matter which. That's the kind of thing you have to choose there. For example, if I say let's choose an arbitrary integer. So integers are all whole numbers, positive and negative. Then an arbitrary integer just means any one of those numbers. It doesn't mean 0.1, but it could mean 1 or 2 or 3 or minus 100 or anything. So maths has a lot of terms that mean very specific things that bit by bit you will get to know. If you read mathematical papers, there will be lots of this terminology that bit by bit you'll pick up on. And it's what makes it so hard to read in the beginning, because lots of stuff is very terse to read and just very tough to decipher meaning from. Yeah, so identity element, I said that 0 was the example for addition because it does nothing. And maybe whilst I sketch this out, you can think of what the identity operation for multiplication would be. So let's move it over to do our groups. So we got our set. We got set, binary operation, an identity element. So let's say that our set was the modular addition. And I say the set was the modular addition, but like the set is actually just the numbers. Modular addition applies a bit more structure and tells us one way that we can wrap these numbers together. But it's actually our binary operation that's going to determine how things work. And in our example, we can do this plus, the addition, and the identity element, like I said, it has to be the one that does nothing, which is going to be 0. Right, and we'll actually usually write these together in like kind of brackets. 0, 1, 2, 3, 4. Addition and 0, and this is a group. Is those things together? Which again, before the first time you see this stuff, it's very strange because it's very abstract. But this is what a group is, and we can play around with some of the things in it. We can do the 0 plus 2. Well, that will give us 2. We could do the 1 plus 2. Well, that will give us 3. We could do the 3 plus 4. Well, that gives us 7. But that's not in our group, so that's something we're going to have to do something about. And because we've got 5 things in our set, this is the same as 5 plus 2, which is the same as congruent to 2. Yeah, mod 2. Sorry, not mod 2, mod 5. Yeah. We could do a different set. We could do 0, 1, 2, 3, 4, 5, 6. So we've got 7 elements in it. And we could instead choose multiplication, which we usually use a dot for rather than the little x. But then there's also the identity element of multiplication. If you thought about it a little bit, you probably realize it was just the number 1. The number 1. Because under multiplication, 1 does nothing. 2 times 1 is 2. 1 times 6 is 6. So it's the one that does nothing. Okay. So those are the 3 things that have to be in our group. But that's not actually enough to be a group. Yeah, a group contains these 3 things: the set, the binary operation, and the identity element. But a group has more structure than this. And I'll get to those things now. But this first group, the 0 to 4 with addition and 0, that is a group. But this second one is not actually a group. It will fail one of our tests. So we now look at what those requirements are to be a group. And firstly, we've got to define something called an inverse element. I define the identity element. If you remember, it's the thing that does nothing under the operation. But our inverse element is going to kind of get you to the identity element. So that sounds very odd. I'll talk about it a little more, but really, once I sketch this out, that will be the clearest way to understand these things. But so the inverse element gets you from your input to the identity element. So if your identity element is 0, it has to be, and addition is your binary operation. It has to be the thing you add to this number to get to 0. So if we work in this first group that I said was actually a group, moving this out of the way. Then let's see. What's the inverse element of 2? So what's the inverse element of 2? It will be the number A. So A is just a stand-in for a generic number. It will be the number A such that, and this little phrase such that is, we use it tons in mathematics to kind of specify some requirement. It will be the number A such that 2 plus A equals 0. Yep. So we're looking for the number that satisfies that property. And as Sarisa, however that pronunciation is right, noted in the chat, this is going to be the number minus 2, because 2 plus minus 2 is 0. Okay. But this does leave us a little problem. Can anybody identify what the little problem is if we use -2 as our inverse element? Yeah. As you've noted, -2 isn't in our set of numbers. We got 0, we've got 1, we've got 2, 3, and 4. So we can't use -2. As far as we're concerned, it's not really a number that necessarily exists in our group or potential group. We haven't proven that it's a group yet. And as Kim noted, it will be the number 3. And why is that? And that's because we actually just have to satisfy this property. And if we check the number 3, as suggested, if we do 2 plus 3, well, that equals 5, which again doesn't seem like 0, but under our modular group, it is 0 because we're under mod 5. Okay, so that's what an inverse element is. Similarly, we can try and do it under this multiplication. This isn't a group, but we can still maybe find the right thing. So let's say we want to find the inverse of just before that, let's just do some notation quickly. So I wrote -2 like this here. That is generally how we will denote our inverse element. If addition is our operation, the inverse of will be the minus. So 2 will be paired with its inverse will be -2. But we have to note that -2 is not in our set, but we can denote the inverse element as being -2, and then we'll have to find what that element actually is. And under multiplication, let's do 3. Under multiplication, we can do divide by 3, or 1/3, or 3 to the power -1. They all mean the exact same thing. But yeah, just note that this number, the 1/3 or 3 to the -1, it doesn't exist as that number in our set in the same way -2 doesn't exist in our set, but we can still denote the number that has that property with this notation. But yeah, let's try and find a multiplicative inverse. In terms of inverse for multiplication, I'm going to get to that in a minute, but let's just first try and find an example of a multiplicative inverse. There's another term we can use. We can say this -2 is an additive inverse because it's with the binary operation, and with the multiplication it'll be a multiplicative inverse. Let's say let's find 2 to the -1. I will usually use this power to the -1 to denote a multiplicative inverse. What does that mean? It means this means we have to find a such that 2 times a equals 1. Okay. And now, of course, you might think a equals a half, the 2 to the inverse, but again, these don't exist in our set. We can brute force it. We can check 0 and 1 and 2 and 3 and 4 and 5 and 6, which is essentially what we're just going to do. But one of these should hopefully be that number. And but bearing in mind that we're under the condition, we're in like the modular arithmetic set, we have that 7 is congruent. It's basically the same thing as 0. So we could just, for example, write out the multiplicative table. We could do where it goes 2, and then it goes 4, and then it goes 8. And then we might pause here and say, well, 8 is the same thing as 7 plus 1, which means it's congruent to 1 mod 7, which is the thing we were looking for. So 2 times 3, sorry, I did powers there. That should be a times 4. I skipped out 6 in that list. 2 times 4, it gives us 8. So 4 is the same thing as 2 inverse. Okay, so these do exist. Multiplicative inverses do exist. And I see you're talking about rings as well. So yeah, if you know that stuff, that's very good. We're going to get onto that more complex stuff very soon. So that's what an inverse element is, just kind of the definition. So what does it mean to actually be a group? Aside from that setting where we have the set, we have the operation, and we have the identity element, we have two main requirements. Every element has to have an inverse. And every element that we can make using our operation has to also be in the set. So in our first example, if we add all these numbers together, we know we can get back to numbers between 0 and 4 because it's modular arithmetic. But in terms of additive identities, we do have to prove that those all exist as well. And we can just brute force that now. We have, how do we get from 1 to 0? Well, that would be -1 equals, it seems like you guys know this decently well, so I won't go into too much detail, but -1 will obviously just be 4. 2 we just did. How do we get from 2 to 0? Well, -2, we know that is 3. And then these actually kind of wrap around where there'll be the inverses. So, sorry, opposites. So how do we get from 3 to 0? Well, it's going to be -3 is the same as 2. And for 4, to get to 0, -4 is going to be 1. Because 4 plus 1 equals 5, which is congruent to 0. Okay, to actually answer your question, if we don't have inverse multiplication, we have a ring. The difference between a group and a ring is, in our group, we have one binary operation and one identity element. In the ring, we're going to have two binary operations, right? Because in a group, we're basically just choosing addition or multiplication or whatever it is. But in a ring, we'll have two operations available. So we've essentially just shown that this group is actually a group because they all have the additive inverses, and everything we can add together is still in our set. But I said that this isn't a group. And does anybody know why? Okay, no comments yet, but this isn't a group. It fails our group test because not every element has a multiplicative inverse. You know, if we do 0 times by a equals 1, what is a? Yeah, this a doesn't exist. You can't multiply something by 0 and get to 1. So as Cerise said, you can't like divide by 0. This would be 0 inverse, which is 1 over 0. So we can say that we can't divide by 0 to get back to 1. So that's why this isn't a group. But if we remove 0, is it a group now? Now we have 1, 2, 3, 4, 5, 6 multiplication, and 1 is the identity element. Would this be a group? Yeah, it is. It is now a group. Okay, I mean we can manually show this. We can 1's inverse is 1 itself because 1 times 1 is 1. 2, well, we just did a minute ago. What was it? It was 4. And we can find it for each number. What would 3 inverse be? 3 would be, ooh, what would it be? It would be 5, because 3 times 5 is 15, which is 7 plus 7 plus 1, and we'll get rid of the 7s. And then 4, we can do this quickly because it will be the opposite thing. Like this will be 2, and 5 inverse will be 3, and 6. 6 inverse, what will that be? Well, there's no other pairing for it, so actually itself, because 6 times 6 is 36, which is 35 plus 1. Okay. So to be a group, every element has to have an inverse element. And that will depend on what the bilinear operation is. I'm just going to wait for this question and then move on. So yeah, if you guys have seen rings and things like that, this will probably be quite basic for you. But the better you understand it, the better. And group theory is like, people who study math, they'll do an entire course on it. And there are much more advanced courses because you can do much more advanced things and have like much more special properties about them in different places. You can have groups of matrices. Elliptic curve stuff will be a type of group. We won't be working with normal numbers, but it will still have the properties of a group. So this set, we're working with normal integers that we know very well, and it seems very easy. But there's no reason why we have to do actual numbers. A group is a generic thing, and that sets can be generic. So if you study group theory, like one set you'll look at is rotations, because if you rotate let's do a phone, if I rotate this like that way, that's different to this rotation, and you can see that these will actually make a group because you can have as the identity element sort of like being flat like this, or let me do it this way, being flat like this, and if I do this rotation once and I do it a second time, I get back to this identity element, this kind of starting point. Right, so there is no reason why the set has to be numbers. It's just like some weird abstract set that can be anything. And as long as it has these properties, every single theory we have about groups will apply to it. So rotational things I think are used in like quantum physics. Like quantum physics will be using groups in a variety of places because it's noticed patterns. You can have groups in forms of matrices. Like they're very generic objects, but so yeah, the more places you'll see them, the better you'll be with them. In terms of your question, Cerise, with modular not being the operation of the group, yeah, because I introduced modular arithmetic to help you understand how we will treat, how we will maintain what we do in our own set. It's like an equality relation that we apply on our set to make sure we stay within it. The mod 5 0 1 2 3 4 is basically saying we'll take this set and have that 5 equals 0. That's kind of the setup from it, and that's how we know that additional multiplication will always give us something back that's inside that set because we have this simple way to work with it. Yeah, it helps us define our binary operation a little bit as well by telling us what we'll get back out. Um, this goes a bit into like some of the deeper stuff that's happening, and I can't answer you perfectly well, but I think it's more a part of actually the addition operation. The binary operation can be defined in any way. I can define, let's do this star thing. This is my own operation, and I will just define it however I want. And I'm going to say 0 and 1 will give us 2. And I'm going to say that if you do it the other way around, it will give you 3. Okay, and if I define every single possible combination, this is a binary operation. Will it make it a group? That depends on like how well it's defined. So the modular arithmetic part is more a part of I think is more a part of the binary operation, because the binary operation, if you do 2 plus 3, sorry, 3 plus 3 is 6. Well, the addition actually is basically just saying 3 plus 3 is 1. Yeah, yeah. Actually, let me think on that a little bit. It's a good question. It's been years since like I've covered the pure basics. We work with this in such implicit ways that I haven't had to question it in like 5 years. Maybe no, maybe I'm wrong. Maybe it's actually a part of the set. So with 0, 1, 2, 3, 4. Yeah, we can do it on the congruency classes. So it's actually 0 bar and 1 bar and 2 bar and 3 bar and 4 bar. So we're not actually working, right? I think this is actually the correct thing. We're not actually working with the numbers 0 to 4. We're working on their equivalence classes. And 0 is the set of all things of the form 0 plus k times by 5. Such I use this colon. It means such that in this formulation, such that this is like normal mathematical notation as well. Such that k is an integer. So this z thing like that. Originally, it's from the German German name like Zahlen, which just means like integers. So all whole numbers, positive and negative. This 0 bar contains everything of this form. So that's 0, that's 5, that's 10, that's 15, that's -5, that's -100. All, infinite possibilities are represented in this set. Similarly with 1, it's going to be exact same, but this is going to be replaced by 1. So, yeah, it's not actually in the operation itself, it's in the set we're working with. Okay, but good question. Okay, yeah, so here's a question. Will we always get a group? Like, is there a simple way to know whether we'll always get a group when we do whole numbers up to a certain point? So that, 0, 1, 2, 3, 4, 0 to 4 is, or 0 to 7, or 0 to 11, or 0 to a million. Is there an easy way for us to know whether we'll get a group? Don't have, yeah, I think we don't have too much time to dig into it, but if it's addition, hopefully you'll see that we'll always get a group. Should be straightforward because we can always have the additive inverse easily. In multiplication, we do have to remove the 0. We can't start from 0. We've already seen that. But we will get a group if the number we go up to is prime. Okay, that's something that we can prove. And that's also why you'll see that the prime's used in so many places. It's because it gives us this special property that 1, 2, 3, all the way up to a prime number, that will always be a multiplicative group. Okay, so if we say that we use a prime here, usually it's because of this fact specifically. It means it gives us a group. Okay, so we're going to speed up a little bit. So we've got fields, and you were talking about rings earlier, and rings and fields are kind of like if you get two groups and smush them together. We have the set, but instead of having one operation, we'll have two operations. And instead of having one identity element, we're going to have two, one for each of the binary operations. Similarly with rules, when will something actually be a field? Well, everything has to have an inverse. It has to have an additive inverse as well as a multiplicative inverse, except for the number 0 because it can't have a multiplicative inverse. And let's just sketch a thing quickly. So the thing we've already worked with a lot, 0, 2, 3, 4. We'll do addition and multiplication. Oops, good dot. 0, 1 to imply the identities. This is a field, and we'll have this notation F5 because it's the field with 5 elements in it. Okay, and we already know that everything has an additive inverse. And everything also has a multiplicative inverse, except zero doesn't, zero inverse doesn't exist. But because that is the additive inverse, it's impossible for it to have the multiplicative inverse. So that's fine. Okay, so groups and fields are quite similar, but we'll just smush them together, two groups together. Again, prime numbers, because of the thing I just said, if we do F7 or F9, sorry, 11, if we put a prime number there, it's always going to be a field. But if we do the 0 up to 9, so we have 10 elements, it won't be a field. Yeah, so F10 doesn't really exist. Okay, so the point is we see the word prime in a lot of places, and it's because of this. It's because of this property. We know we'll get a group from it, or well, a field also from it. Yeah, so field is the group with two groups smushed together. You'll have two operations. And we're only really in cryptography. We're just interested in finite fields and finite groups. You can have infinite groups, but we can't work with those properly in cryptography. Okay, so we're now just going to touch on polynomials again, and then I'm going to give you a lowdown of something called the Schwartz-Zippel lemma, which is very important for PLONK. We actually already looked at polynomials. We said that we've got 4xy plus 3x minus 5. We can have multivariable. We can have x and a y and a z, and any number of variables. In PLONK, we're only interested in a single variable, so we'll just do like x's. But the number in front as well is also going to have a limit. We have four in this example. We have a 4 and a 3 and a minus 5. Under our circumstances, we're only going to allow coefficients that are from a field. So if we work in F11, the field with 11 elements in it, then the 4 is fine and the 3 is fine, but we can't have minus 5. There will be an equivalent since 6 plus 5 is 11, which is the same thing as 0 in our modular arithmetic set. Minus 5 will actually be the same thing as 6. Sorry, Kim, I don't know if you're asking a question, Kim, if you're saying you've forgotten the difference or if you know the difference now between rings and fields. Not understood. I haven't explained the difference. And that's because, like, in cryptography, we don't really talk about rings because they don't have the property, they don't have the useful properties we want. We want the things to be fields because they have such useful properties. I'm actually just checking myself quickly because I'm pretty sure from memory that the ring is the same as the field, but everything doesn't have to have a multiplicative inverse. I think it has to have an inverse for the first binary operation, but not the second. So F10, for example, is not a field, but it's a ring because 2 times 5, 2 and 5 don't, 2 doesn't have a multiplicative inverse. I can show you that quickly. If you try and do, let's just do a small of, well, yeah, 0, 1, 2, up to 9. So we've got 10 elements. And we have that 10, same as 0, 1, 10. Yeah. So yeah, under this scenario, what is the inverse of 2? Well, 2 basically 2 times a equals 1. What is a? What is a? Under this setup, A does not exist. There is no such A. 2 does not have a multiplicative inverse. Okay, so this can't be a field, but it will be a ring. The reason why it can't be, why 2 can't have a multiplicative inverse is because numbers can be one of two things. They can either be a multiplicative inverse, which we call a unit more generally, or they can be something called a zero divisor. But because you can do 2 times 5, which equals 10, which is the same as 0, because you can get from 2 to 0 by multiplying it with a number from the set, it means that it can't be a unit. I'm not going to get into that stuff because it's out of the scope. Like I said, we never read about rings in cryptography, or extremely rarely, because they just don't have the properties that we're interested in. They're not conducive to doing the things we want to do. So in the ring, you don't have to have a multiplicative inverse for everything. Okay, but the polynomials, let's do that one. 4x squared plus 3x minus 5. 4x squared plus 3x minus 5. Like I said, if we're working in F11, then 4 is in the set, and so is 3, which is fine, but minus 5 is not. But we know that minus 5 plus 6 equals 11, which is congruent to 0 mod 11, which means that, minus 5 equals, or is congruent to 6. So we'll convert this polynomial to 4x squared plus 3x plus 6. Okay, so all these coefficients have to be from the field that we've set for our polynomial. And we refer to this more generally, all these polynomials, we can define what we represent with this notation, F11, square brackets, x. This means like all polynomials of that format. We can have 3 plus 7x, 53, sorry, not 53, because that's not in F11, obviously. 5 plus 10, x to the 1,000, and, plus any other term. But this notation means all polynomials of this format. Yeah, this is what we just did, this notation. We've got the term polynomial degree. We did the minus value, so that's fine. The polynomial degree, the degree of this polynomial is 1, because the highest power of x is 1. If we write on x on its own, it means that the power is 1, as you probably know. Here the degree is 2. Here the degree might be 1,000, because I've got this plus dot dot dot. We don't know what comes afterwards, but we know that it's at least 1,000. Right? And I've mentioned before, but a lot of what we do in proof systems is with polynomials. Representing numbers as polynomials, checking that polynomials behave in a certain way, checking the degree of a polynomial, seeing its highest degree, proving that its degree is upper bounded by some number. Right? So polynomials do a lot of things, which is why we want the coefficients to be fields, because then we know that they'll have certain properties, useful properties. When we evaluate the polynomial as well, the number we'll get out will also be in the field. Like now, everything we're doing isn't with normal numbers, they're with field elements. So let's do this. Let's do f of 3. Well, that's 4 times 3 squared plus 3 times 3 plus 6, which is 4 times 9, which is 36, plus 9 plus 6, which is 51. And then what's this? Well, we can't just have 51. We've got to know what congruency class that's in. And that's in, what is this, 44/7, not 11, right? Because this is equal to 4 times 11 plus 7. Okay, so we don't work with normal numbers in cryptography. We're always in some sets, usually a group or a field. In elliptic curves, we go from a field into the elliptic curve group, which is actually a group. So it doesn't have, it only has, this is actually one annoying thing about elliptic curves, is that because it's only one operation, we sometimes do it as additive notation and sometimes as multiplicative notation. And it can get a little bit mixed up there because it's only one operation. And elliptic curve group isn't like normal numbers. It's unclear whether it should be additive or multiplicative. Yeah, so that gets a little annoying. But yeah, we do a lot of stuff in fields. Okay, so we're almost done. I just want to go over the core idea of the Schwartz-Zippel lemma, and then we're done. We actually just removed this from this lecture because it's quite complex, and this lecture already took a bit of time. But I kept one slide because I wanted to go over like the core idea. And if you recall, I said that in a proof system, the actual proof says this statement is true with probability 99.9999999. And this 99.999 whatever, the error term is the 0.0000 to 1. This comes from this lemma specifically. And this lemma relates to polynomials and stuff. So the the the, the intuition is, if we're to sketch out our polynomial, and so we have f of x, arbitrary polynomial. We don't know what it is right now. If we sketch out what it looks like, it will do this sort of thing. Yeah, there's a few things I mentioned here. So I do sketch out like this, but remember, this isn't actually entirely true, but it helps for the sketching because on the bottom, we're not working in normal things anymore. We're working in a field, FP. Same on the top. Same on the top. So if we have 0 and 1, what are these numbers in between? Well, in a field, they don't exist. So I'd have to sketch a value here for the function, and then it'll be here. But I can't draw a line between them. So when I sketch the function, it should actually just be, a dot, a dot, a dot in different places. But that's really annoying for intuition, right? So for intuition, we're just going to sketch it as an actual curve. Okay. Now, if we get a second function, g of x, if g of x is the same polynomial as f of x, if it's the same polynomial, what will its curve look like? Well, obviously, oh, cool. If it's the same polynomial, the curve's going to be the exact same. This green is going to be the exact same. Of course, more same than I'm drawing it. Okay, so if we evaluate, if we pick a random number, tau, and I say, does f of tau equal g of tau? Well, if they're the same polynomial and tau was here, then obviously they're going to have the same value here. And if tau was here, this would be the same value. If it was here, this would have the same value. At all these points, obviously, f and g are going to have the same value. But what if you have another function, h of x, but it's not the same as f and g? What will its function look like? Well, its graph look like? We don't know exactly, but it will maybe do this. Okay. So if we now do the same thing, a random check, if we do h of tau equals f of tau, will we get the same value? Well, here in this first one, no, those are apart. What about in the second one? No, those are different values. And this third one, those are different values as well. In fact, if they're different functions, different polynomials, they will be different almost everywhere. What's the percentage likelihood of them having the same value? It depends on the size of our field. But if we have a f to the 2 to the 256, a massive number, the likelihood of them having the same value is tiny. It is 0.00000 whatever percent. That's exactly where our term comes from. In a lot of our proof systems, in PLONK, we evaluate polynomials at random places. And if they're not the same polynomial, we will get out different values. And that's how we do our verification. If you were honest, if the prover was honest and did everything correctly, we have an expectation of what their polynomial valuation will be. But if they try and cheat, if they're not doing computation honestly, they will fail this. The polynomial will work out to the wrong value. Okay, there's a lot more maths behind that to prove it, and to give you the to get the actual percentage, it's straightforward. It's the size of the field you're working with and the degree of the polynomial. But yeah, that the statement, the very specific statement in our definition of proofs, the percentage comes from this. Okay, so we've added in a bit more detail. We drew out the circuit with gates and wires, and we put in the values. Then we turned the values into polynomials. Then we committed to them. Then we sent them. Then we evaluated those polynomials again at random values. And then that's actually kind of what we're using here. We're going to compare those random values to see whether they have this property. Okay, using this Schwartz-Zippel lemma. So not every proof system will do it like this. They won't use the Schwartz-Zippel lemma, but PLONK does, and so do a bunch of others. Okay. Okay, so that's it for this session. I've not really been setting homework. It's more of an optional thing that I'm recommending things to do. At the end of last session, I spoke about Anki and memory, and how unless you review stuff, you'll just forget most of it pretty quickly. So if you want to take up that advice and you want to use Anki and you want to remember stuff from this session, I would recommend you make some cards on these things. Some of the art of Anki and memory is like figuring out what to make cards about. So if you know something pretty well, maybe you don't need a card, but it's for the things you don't know as well. Like, what are the definitions? What are the rules you need to satisfy in order to be a group? What is it? A field? What's the definition? What's the difference between a field and a ring? What's the main idea of the Schwartz-Zippel lemma? Anything like this. So it would be good for you to go and make those cards. Our last session, where we're going to do some more math, see some more advanced stuff, which is the elliptic curve group, will be this Thursday at the same time. So Thursday starting at the same time. Yeah, and then we will be done, and you will have a lot more knowledge about how these systems work and the tools behind them. Again, I mean, these are very complex systems, and to actually understand the systems, you've got to put these tools together in very complex ways. But we're just covering what those items are to start with. Cool. Any questions? Good. Just waiting for the typing. Thank you, Lorenz. Thank you, Lautaro. Thank you, Ashok. Yes, same time on Thursday. Okay. In the trusted setup context, how can the key be the backdoor for the false proof? How can the key be the backdoor for the false proof? Right. So that will be easier to explain next session because it in this Schwartz-Zippel scenario, we want to make we do our test at the end by checking whether our polynomials have the same value at some random number tau, right? And we don't know where tau is, it could be anywhere. If you know tau, if you know what the random number is going to be, you can make your polynomial, well, I'm going to draw it. I can make my polynomial. If I know here is where tau is going to be, I can make sure that whatever polynomial I make crosses over at the exact place. Okay? So now my polynomial is definitely different, but I designed my polynomial to do anything I wanted, but just have one condition where at tau specifically, it has the value that they're expecting. So if I know tau, I can cheat. Now in the trusted setup ceremony, again, I can explain, that will make sense next session. We will make this random number tau, but nobody will know what it is, which is strange because, once we know it, how do we not know it? And that's because it's not a number, it's an elliptic curve element. It's in an elliptic curve group. So it will be a number, but it will be like the elliptic curve group element added to itself tau times. So we have a group element, but we don't know what the actual value is. And it's a very odd thing because it's a random number we make, but we can keep using the random number and it will stay random even though it doesn't change. But yeah, that will be a lot easier to understand next session. So please ask that again next session. I mean, there's a good chance I will explain it anyway. But yeah, in terms of actually how you can how it's a backdoor for the false proof, if you know where it's going to be evaluated, you can just cheat very easily. The kind of key thing going on here is that tau is random. So if it loses the randomness, you can make the polynomial that matches it at the right place. Okay, cool. Nice work, everybody. I will see you all on Thursday for the last session in the second half of the maths.